Thank you so much. I hope you can see my full screen. And greetings to everyone who is whichever part on this planet. So appropriate greetings. As you can see, this title does have time machine, and that sounds very fascinating. But I do want to tell you that everything is happening in astronomy in the past. Even the sun rays which are coming to us are taking 8 minutes. And when we talk about, many of you work in galaxy and those kind of interstellar medium. So many of you may realize when we say that galaxies, we saw these merging galaxies, we actually saw those merging galaxies billions of years ago or millions of years ago, and the light reaching us now. So, in what state those galaxies are, we don't know about them. So everything is happening in the past, and just with handful of physics laws and handful of photons and now gravitational waves and neutrinos, we are trying to decipher our universe. And in that quest, I'm trying to do a little bit with massive stars. And having said that, I will show you this diagram, because if you take a star cluster and if you rearrange it in terms of increasing luminosity and decreasing temperature on the right hand side traditionally, so increasing on the left hand side, you will see that stars are not randomly placed. They occupy a very, very, well defined place. And it looks like a structure, and this happens to be one of the most famous diagram in astronomy, and it is called Hertzsprung-Russell diagram or HR diagram. In this diagram, our sun is, you can see with this place, and sun is a very average star in our galaxy. And we all know that nuclear fusion is what is, providing the light, and because of which we survive. And this is hydrogen fusing into helium. And sun has been burning hydrogen into helium for past 5 billion years and will continue to do so for another 5 billion years. But when it exhausts its hydrogen fuel, what will happen is that sun will become a red giant star and then leave its outermost layers as planetary nebula and become a white dwarf. So that is the fate of our sun. But that's not what happens when we come to massive stars. Massive stars, as you can see, lie on that blue strip of the chart diagram, and these stars are having advanced nuclear fusion states, not just hydrogen fusing into helium, but all these heavier elements are also being, synthesized inside these stars. And when all of the fuel will get exhausted, then the star will undergo a gravitational collapse under its due to its own huge mass, and then that will result in an explosion which we call supernovae. And that's what the topic of today's talk is. But in some, I just want to touch base on this aspect that in some cases, if the matter ejects, it has a directional preference, or it ejects in a very confined directions. This is called gamma ray burst, and we got to know about these gamma ray bursts just 50 years ago. So these are pretty new phenomena. They are both are manifestations of death of massive stars, and this is what we are going to explore today. But today I'm going to be mostly talking about supernovae. But I just wanted to add this, that I just said that sun will have fuel to go for it to go on for 10 billion years. But massive stars, for example, a 15 solar mass star will live only for a few tens of million years. And if you look at this is stable that these advanced nuclear burning stages happen for progressively smaller amount of time. So it is a very short-lived star, and when this the synthesis is happening inside the star, and when this star explodes as a supernova, that's when all these elements come out and become available to form. And so when the next generation stars are formed, like sun and the planet Earth, and that's how the life is formed. So all of these elements, most of these elements, are synthesized inside this massive star, which is what we are made up of. So we are literally made up of stardust. Um, um, I would also like to just add for completion that in the current traditional picture or our understanding, supernovae leave neutron star behind and gamma ray bursts leave black hole behind. Of course, there are alternating theories about magnetars and other things. But this is a very traditional picture, and we do know about neutron stars because they give this lighthouse effect, and they rotate and they pulse, and we see them as pulsars, and which is a different field of astronomy altogether. We had we had conceptualized black hole, but we had not known about it until 2015 when LIGO, gravitational wave detector, saw gravitational wave from merging of black holes. So now black holes, even if you're sitting in the front row, you won't see a black hole happening, a few kilometers down the line because it's not emitting any photons. So gravitational waves are probably the only way to see these black holes, and that's how we see them. So now, since supernovae is the topic, I would just like to say that we do like to study supernovae because of these heavy nuclear synthesis. They do enrich, they do participate in chemical enrichment of our universe. They are probably the only laboratories in the universe where you can study extremes of physics, where we are talking about relativistic velocities, electrons, which are, 500 kilo electron volt rest mass reach GeV energies, the magnetic fields become, extremes. And I see Prakriti has her hands up.
Yes, just one small question. Um, is gamma ray burst also happening in pulsars, which is like the end state of
We don't
positive?
currently we don't think that gamma ray bursts make neutron stars. So, neutron stars are the ones which are like, product of like end product or remnant of supernovae in the current understanding. We do think that some gamma ray burst magnetars are at the center of those gamma ray bursts, but
That
not
probably
immediately.
happens later after the formation of pulsar.
There are various theories about that, and people worry about those things, finer details. But this is just very introductory picture of supernovae and gamma ray burst, how we understand them to be.
And just one another point to clarify, are you okay with people asking question in
Oh,
between?
of
Yes.
course,
Yes.
it's a
So
very important.
to
Yeah,
others, please feel free to raise hand and talk to.
I won't see the hands actually. So if you,
I will always take a look of that. Yes. Okay.
I do want to say that since we're talking about supernovae, we don't know which part of the sky the supernova will explode. So unless, very few supernovae were known in the past. And if you can see in this very little, font, the year is mentioned at the lower part and the supernova, we just knew few, but now that we have the robotic telescopes, which are scanning the sky and looking for new sources in the sky, we kind of know many more supernovae. And we do know from the physics and our understanding of massive stars that there are around 4 to 8 supernovae exploding every second in our universe. So that's supernovae. But that's not the topic of this talk. The topic is what is circumstellar interaction, and that's what we're going to talk about. And if even the sun loses its mass, outermost layers, which are less gravitationally bound. So these less gravitationally bounds are lost into the medium. But mass loss rate from sun is 10 to the power minus 14 solar masses per year. But from massive stars, this can be orders and orders of magnitude higher. For example, 10 to the power minus 5 or minus 6 solar mass get lost every year, which is moving with tens to hundreds of kilometer per second. So this is still, sticking around the star, and which we call a circumstellar medium. So this is different than the interstellar medium, which doesn't have to have any objects around them, but the medium or matter around the star is called circumstellar medium. And if the supernova, now this star explodes as a supernova, and this the shock wave of the explosion is moving with tens of thousands of kilometer per second. Because of this physics, it creates a shock, and which we call a forward shock, the blue one. And because the deceleration of the shock, there is a reverse shock which also gets created, and these different shocked regions produce multi-wavelength emission. And if one studies, one can this is basically called circumstellar interaction, and it emits in multiple wavelengths. So one can learn about these shocks, these ejecta, explosion ejecta, and the surrounding wind in great detail by studying supernova post explosion in via circumstellar interaction. And why is it called time machine is because I just said that the winds are moving with just few tens of kilometers per second, but the ejecta is moving with tens of thousands of kilometers per second. So you can imagine that, if you're going in a direction by foot and somebody is following in a car, one can actually trace, much farther away and see many, many more people who are walking on foot. So it's exactly like that kind of effect. A wind which is lost or matter which is lost from the star just a day before, like a year before explosion, can be traced just a day after the observation of supernova, or so on and so forth. And that's why it is called a time machine effect. And why do we study that? And for that, the reason is that there is this massive star which we see a lot in our galaxy and outer galaxies in some cases. We see the supernova explosion by our robotic telescopes and we study them. We also do a lot of simulations. But the physics becomes so complicated just before the explosion that we really don't understand the complexities just before the explosion, which is happening on a time scale of milliseconds or so. So there is a big, but the thing is, we do know that this massive star will result in different kind of explosion, and there is, this is just again a traditional picture of type of supernova, but there are many, many more type of supernovae, and what kind of massive star is leading to what kind of supernova is not really clear, and there is this gap in our understanding, which we are trying to fill that gap. And the problem with that gap is that we do know that sun is losing mass and sun is fusing hydrogen into helium, but in these massive stars, these advanced nuclear stages, burning stages are going on. So the radiation pressure is different, nuclear fusion is different. So there, the mass loss rate even can be non-linear, or we don't understand what kind of masses are being lost, or whether it is constant or it is changing with time. How is it changing? So as a result, what happens is there is no mapping between a zero mass H sequence star to its final end product just before supernova explosion. And that causes uncertainty, that causes loss of information, and it's not a good state. So for example, if you look at this diagram, on the x-axis, this is the zero H main sequence star of a given mass. On the y-axis, the ratio of the mass lost to the zero age mean sequence, and you can see the uncertainties are as large as 50, 60%. And this is just assuming a constant mass loss rate. But there are complexities due to, stars may live in binary, which we know happens very frequently. The star may have magnetic field, which we know 10% of our Milky Way massive stars do have dipolar magnetic field. The rotations may be different. The galaxy has different metallicity, and of course there could be asymmetries of various kinds. So what actually eventually happens, that we are losing all track of, what kind of star is losing what kind of mass and exploding in what kind of supernovae. Of course, you can talk about the archival images, and you can say that, for example, in this image, you can see a supernova exploding in images between 10 years down, difference, and you can see there is a supernova. But archival images will just reveal moments before the death. It won't reveal the whole evolutionary stages of the star. And also, they are limited to nearby supernovae because the massive stars are not as bright as the supernovae. So you will see massive stars only in very, very local universe, not too far away. So with that, I would say that there comes that why do we study circumstellar interaction is because the mass lost from the star is carrying the footprints of the star, carrying the information of the star. And if you are studying by ejecta hitting into the this wind, this mass loss from the star, and studying in multiple bands, wavelengths, we are actually understanding what kind of evolution the progenitor had. And longer we study these things, farther back in time we can go. We can even, go to carbon burning stages, not just silicon, and late stages. And depending upon what is the ejecta speed of the explosion and what is the wind speed of the material lost from the star, the look back time can be different from different kind of supernovae. Of course, I'm saying type 2p, 2n, and 1c. Just don't go into those details, but they are all, the classification is not very, profound classification. It is just based on optical spectra and light curve, what we see, and then we classify them in different classes. So the look back time is different, but the point is that longer you study them, far back time you can go, and you can actually start to map the progenitor evolution, and that this kind of star living in this kind of galaxy having, this kind of yeah, physical conditions will result into this kind of a supernova. So that kind of mapping is done, and that's what we do. So the question comes, how do we do that? And of course, we do that at different time scales. For example, at if we do observations for 1 week, we can go, we can go up to say 1 year before the explosion, depending upon the ejecta and the wind speed, and we are tracing the CSM radius around 10 to the power 15 centimeter. That is how much the wind we are tracing. We can also, if you do months observation, if you do the circumstellar interaction studies for month, you can trace 10 years before the explosion, or similarly, 100 years or 1,000 years. So basically, how far, observations, if you do observations for decades, of course, very few supernovae have been observed for decades, but you can go back very early progenitor histories of these supernovas. So I will actually go in the house study about how very beginning to the end. And the first is flash ionization. This is this actually literally tells you the moments just before, dying moments of the star. And flash ionization is relatively new physics in terms of observations, because observing supernovae that early with very good telescopes have not been always that easy. But what is flash ionization is that it is understood that if a supernova ejecta is, after the explosion, gravitational collapse, this explosion happens, and when it reaches the stellar surface, the shock breaks out, and in that moment, there is this huge radiation which is ionizing the emitted CSM, circumstellar medium, surrounding the star and creating these narrow emission lines. And this is flash ionization. Of course, shock breakout is also something which has been envisaged for a long time, but it was only once, and only once it has been uh, discovered. Yes, Pragati?
In the previous plot, what is the X and Y axis? Like what is being plotted?
Oh, this is basically on the x-axis. This is wavelength,
Hmm.
and on the y-axis, I'm just showing the normalized spectra at different days.
Okay,
So
okay.
you can see, for example, on 0.26 days, there are a lot of narrow emission lines, and as you go later and later, these narrow emission lines are just vanishing. So flash ionization is just the moment star comes out, it ionizes, and you see this narrow emission line, and
Are the
then
same lines becoming broader or it's just
no, there are different lines. There are, yeah, these are higher ionization lines in the flash ionization, and later you are seeing the regular what you see the spectroscopy of supernova, where you will see if it's hydrogen, rich enriched. You'll see H alpha, H beta lines, and then other lines of the supernova, but a traditional spectra of the supernova. But I was going to say that the shock breakout has been seen only once, and only once in real time. And what was happening that we were doing a swift observation of a supernova 2000 UY, as you see on the top plot. And then we, instead of 2000s, with Swift XRT, and we saw this. If you see on the bottom, you see, I don't know why I don't have my cursor here, but you can see this big outburst, which we am calling 2080. And if you see the light curve of that, you will see that it peaked very fast and then declined very fast. So that's the real time shock breakout which has been seen so far. But the point is that because of this shock breakout, we do see flash ionization, and they disappear in within few days. When you do the apply some physics and study them and derive some parameters, you see that the mass loss rate is much higher than a traditional star, and like 2 or 3 orders of magnitude higher. And I think it's so this is already in conflict with the traditional supernovae theory, where mass loss rate is assumed to be constant, and then people derive parameters, because we now see that these mass loss rates are higher, and people try to see what could be the reasons. Of course, binarity has always been invoked whenever the mass loss rates have been not what people thought them to be. But just before, explosion, you have this increased mass loss rate that kind of tells that maybe it is coming due to maybe advanced nuclear burning stages rather than some external factor like binarity and so much. And this is a very recent case, is a very famous supernova 2023 IXF, and I think anybody working in this field would know about this supernova because this was the closest supernova in a decade. For a week, flash ionization features were seen, very high mass loss rate was seen, but then we actually applied for Chandra time and we observed two epochs. And you see that after that, the yellow part is where our Chandra observations were taken, and we see much lower mass loss rate. We not just that, we actually see a constant mass loss rate. So, so you see this flash ionization feature, and then you see a very regular, traditional, and boring mass loss rate. So those kind of things have been seen, which has told about that there is a circumstellar medium just surrounding the supernova, which is a confined CSM. Now I'll move on to X-ray emission, which is probing slightly further away than flash ionization. I would call around 10 to the power 16. And X-ray emission is simply coming because when these shocks are created, these shocks are super hot. Forward shock is around 1 billion Kelvin, reverse shock is around 10 million Kelvin. And X-ray emission is thermal. It is just a factor of what kind of density the shocks have. And since the reverse shock is of at least order of magnitude higher density than the forward shock, the reverse shock usually ends up dominating the X-ray. And many supernovae have shown, kilo electron volt kind of X-rays from supernovae, and Chandra, XMM, Newton, and Swift XRT have been really pivotal telescopes for studying supernovae in X-ray bands. And since X-ray luminosity depends upon the density, and density is created by the CSM, one can actually study the CSM and see the progenitor evolution, because when the supernova exploded, the ejecta speeds and wind speeds from the optical measurements, and one can just trace the mass loss rate back to the star. But there's things are not that simple, as I would say, because when the density is very high, based on the parameters, how the ejecta structure is, how the speed is, how the mass loss rate are, there could be cooling, and the shocks could be radiative. The reverse shock can be radiative, and if that's the case, then the luminosity will be, will have, it'll just be a fraction of basically kinetic energy of the shock, and then you will see that is proportional to density, and the radiative reverse shock have been seen in many supernovae. For example, long time ago, we had studied this very famous supernova 1993J, and we combined all the X-ray data that there was available that time, and we carried out the modeling, and we saw that for 5 years, reverse shock remained radiative, and hence the X-ray luminosity we were seeing was just coming, uh, you know, by a different mechanism than thermal bremsstrahlung, which is what took over after 5 years. And when we modeled that, we actually showed that our physics is insufficient to explain these kind of supernovae, and we really need to get into more complicated models of multiple temperature, which is still being, it's not yet very fully developed, and it's still being considered. But I would like to move to the next part, which is what happens sometimes the density of the reverse shock is so high, and the reverse shock becomes radiative, that the region between the forward and the reverse shock, which we also call contact discontinuity, that absorbs all the reverse shock X-ray emission, and nothing comes out. And in that case, the forward shock, which is also high enough density, takes over, and the forward shock emission is dominated by supernovae. In supernovae, and we know that this is forward shock emission because if you look at the right hand side diagram, KT, the temperature, there is no upper bound to this temperature. And there is no upper bound because this supernova has been observed in Chandra and XMM energy range, and which is 10 keV upper limit. So a plasma which has a temperature much higher than 10 keV is not going to be represented by this. So you really cannot constrain the temperature of the plasma. In that case, the new star has been revolutionary telescope we only have one neutron star, but it has changed the field. And when we combine the data from XMM and new star, in some supernovae, we have seen that we are able to actually very precisely constrain the temperature of the shock. And as you can see, sorry, as you can see in this case, the temperature is very well defined. So of course, there has been some studies, like for example, a very famous supernova 2014 C. It is also a gravitationally collapsed supernova where observations took place. And this I would just like to say that these plots may sound very simple, but they are not simple because getting X-ray time on an object is so expensive, so rare, so difficult, and getting the time for it, like 10 epochs is almost unprecedented. I think there is no other, very few supernovae which has been observed so many times with X-ray telescopes because you just
Monami
don't.
has raised a hand.
Okay, yeah, Munami.
Yeah, I have a question, maybe very naive question. I think in the previous slide, you have shown that from the spectra, you had calculated the temperature of the shock, right?
Yeah.
I mean, is it like, are you feeding the spectra with 1T temperature like model, or like have you tried multiple temperature and then come up with this best fit of temperature?
Yeah, so actually currently as I showed, so sorry, I'll just go back to this where I'm sorry. So here this is a result of simulations where we had tried to do a multi. So in this case, long time ago, we created this stable model and imported into XSpec, and it was a very rudimentary model, but it did show that multiple temperature fit the data better. So shock should have multiple temperature, but XSpec deals with single temperature plasma, and that's what has been fit in all there. Is basically simply just because the shock is hot, you will have this thermal emission, and thermal emission will peak at a certain temperature. So that's what. So it's, again, I would say it's a simple model, and more work needs to be done if somebody is willing to put effort and time. So but yeah, it does give you some sense of that. If you average the temperature and take the dominant single temperature, that's going to be around 20 kilo electron volt in this case. And since if you do the physics, hydrodynamics, the reverse shock cannot be at 20 kilo electron volt. The emission must be coming from forward shock. But we know that reverse shock is moving into the ejecta, so it is much dense medium. So there is, and since X-ray depends upon density square, there is no way for reverse shock X-ray not to dominate unless all of it is absorbed. Right. So by using these kind of arguments, we are able to constrain some of the physics of these things.
And I how these numbers, like if let's say you previously you have done with like some multiple temperature component, but I think I understand that in expect there is like you can fit with 1T model, but how these temperatures compare with each other, like is it like different? I mean that those multiple temperatures, I mean range is different than this single
Not
temperature.
more than order of magnitude, because shock is at a very high temperature. You may have some lower temperature or higher temperature components, but they are still not more than an order of magnitude. But again, I would say more studies are needed in this direction, and we have simply not done it. The person we were collaborating, that person left the field, unfortunately, because.
Physically, if it's radiative shock, you do expect some multi-phase.
Yeah, yeah, exactly. So that's why we had done this radiative shock in this case, and it was again a rudimentary model which fit well. But this is reverse shock radiative, and now I have moved to the forward shock, which we are still not sure is radiative or not, because remember, forward shock is still at lower density, and cooling time may still be long enough that
Got it.
it's
Got it.
much longer than the dynamical time scale of the supernova. So this is still going well with single temperature model. In this case, for example, it was seen that the shock is at tens of kilo electron volt even after revolution at different epochs. But when you when one did the calculation, the cooling time was larger for forward shock, and hence it was still adiabatic. So it's not a bad bad approximation.
Ah,
But I am coming to radiative forward shock, because in this particular case, we had seen that the forward shock, the density was just so crazy high that the shock was radiative. And you see, I'm talking of the especially that the first epoch where the column density was 1,000 times larger than the galactic column density, and when we calculated, it had to be radiative shock. And then, of course, our single temperature approximation is not really a very good approximation. But we do see that this is, at least we still get a lot of information, because if you look at this spectra, we do see 6.4 keV fluorescent iron line, which can only be coming from the reprocessed material. And that means the density from which it is getting reprocessed should be pretty high, and one can actually constrain the density from that. So we do see evidence of that. In fact, I would say we see the evolution of the evidence. Like, this is again this 2023 IXA, where in the first epoch we do see this 6.4 keV line, and we don't see in the second epoch, which means for a short amount of time when the CSM the ejecta was very close to the star, the forward shock was still radiative, and sorry, but then it ceased to be radiative, and then the adiabatic approximation was good enough. But in this particular case, one of the case we did observe, you know, I'm
You can
sorry,
also constrain the distance
we
from
know the distance of the supernova through optical spectroscopy,
know
right?
how fast this material is moving out from.
Yeah, so the optical spectra, the narrow lines will tell you the wind speed, and the ejecta speed can also be obtained from optical measurements, and so you know how fast they're moving. We exactly know all these things, yeah,
okay,
at
okay.
least in this case, yeah, especially for all within 50, 100 megaparsec supernovae, all these things are pretty well defined. But anyway, here I'm showing you the six X-ray spectra of a same object, mm, and you can see that how different it can be just within a month or 2 years, and so. And all of this is different because they are showing different column density, and different column density points are obtained. And this exactly tells you that how the medium is, or how in some way the this is like days since explosion. So it means you have to translate it to years before explosion. And you can see that, the mass loss rate, when I'm showing 1,000 days, must have been much lower. And then it had an enhanced mass loss rate leading to the explosion. So it can already say that the bigger picture is already, is very different than the simplistic model assumptions and so on. Um, okay, so moving on beyond that, since I'm just giving you a glimpse of how these studies are done, I'm not getting into too much detail into everything. I will move on to the second thing, that X-ray we assume so far has been only thermal, but there can be non-thermal X-rays also, because, for example, there are supernova which has huge amount of presence of photons, and these optical photons can be inverse Comptonized to X-ray energies, and that can create a non-thermal emission. And it has been seen in few supernovae, mainly on those supernovae which show a lot of hydrogen in their spectra. So the non-thermal X-ray also, first of all, one has to disentangle the non-thermal and thermal part before being able to do any physics. And which may sound very simple, but is very difficult, because remember, we are dealing with X-rays, and the photons you can count on your fingers. You don't, there are supernovae we literally get like 20 photons or 30 photons, and optical astronomers will never perceive the idea of counting like 20 photons or 40 photons or even 500 photons, because that's just not how. But in X-ray, this is how we do. So disentangling is not really that easy, so everything is taken with a grain of salt, because it's very difficult to do these kind of modelings. But my point is that how X-ray evolves does tell a lot about how progenitor evolved. It constrains the densities, it constrains the temperature of the shock, which depends upon the ejecta speed, which depends upon the explosion energy, and so many parameters. So if one can carry out these studies, different studies, one can actually constrain a lot of parameters in these supernovae. And now I'll move on to radio emission, because radio emission is the longest lasting emission. Radio emission is happening because when these shocks were created, in these shocks, magnetic fields were amplified, electrons were accelerated to enough high energies that non-thermal synchrotron could be triggered. And non-thermal synchrotron, since it depends upon the acceleration of electrons, which happen much more in forward shock, which is at a much higher temperature, radio emission almost always come from the forward shock or the fastest ejecta, and it is synchrotron in nature. I've already told you. And but radio emission also gives different kind of information. For example, if you study a different kind of supernovae for a very, very long time at different frequencies, different light curves and spectra, one can actually kind of understand different kind of progenitors of these star by just you take our Milky Way stars in different special phase, and then see there like how these stars should be at given point of time, and stellar evolutionary stage. And of course you make some approximations, and you can see that what kind of stars must be creating what kind of supernovae. And these are like these three major points I have like curve I have plotted out. There are three different kind of supernovae, and so they do give us some information. The interesting aspect is that radio emission, because it is synchrotron is nature, synchrotron will be self-absorbed, and that self-absorption depends upon the magnetic field, and that gives information about magnetic field and the size of the supernovae. And that has actually told us a lot about, in fact, another way of finding the speed of the fastest ejecta, and of course the magnetic field amplification. So that does tell us about the what kind of acceleration processes are taking place. And these are the highest acceleration sites in the universe. We also, if the density is very high, you will also do free absorption of the radio emission, and that, since that depends upon the density of the medium, it directly tells you about the mass loss rate of the star. But we have actually seen that and this was first we published in 2012. This was also seen, but now we see in so many more supernovae. We have seen that if the density is so high and the shocks are radiative, that there is some mixing of cold plasma into the shocks itself, and then they do internal absorption of radio emission. And that has been seen in some supernovae. And so basically my point is that if you study the rising part of the radio light curve or radio spectra, one can actually get the whole lot of information. Of course, the falling part is also important. That tells us about the P, which is the electron energy index, but the rising part gives a lot more information. And we identified this, and that's why we are having, for past few years, we are having this program with the GMRT low frequency investigation of massive progenitors of supernovae explosions, GLIMS, which is a very successful program. It is, supporting several PhD theses and a lot of master's thesis, and getting very interesting results. And we actually have a web page of all the supernovae we are observing with this. And it's given us a lot of information. So for example, I'll just like to point out the work by my current student Rafael. Rafael has done this is, I think, the first study where it has such a detailed study of its own kind in a supernova, where we had 5 epochs of Chandra observation, few epochs of Swift observation, several VLA and GMRT observations, optical photometry and spectroscopy and infrared observations. And he actually carried out this study for more than a year, and the paper is in archive now. And by different inputs from different wavelengths, we are able to derive a lot of parameters. But one of the things which we were able to do is derive mass loss rate from different different wavelengths, and we do see that they actually don't match. And this is always the case when you go into details of a study. You do see that the things do not match as the theories thought them to be. And that, I think, we have explained that it's certainly, all of these models work when you assume a perfect spherical symmetry, and here we were able to nail down many other parameters. So we did identify that it's the asymmetric mass loss rate from the star which may be causing this thing. So this paper is, in fact, Rafael is going to submit the referee report, like revised next week, and hopefully, this will be in print very soon. Other thing I'm going to go is that very late time studies. If you manage to get to observe these supernovae for decades after the explosion, you can actually get back to even very early stages of progenitor, even the helium burning stages. And radio is much easier. X-ray is difficult, but we have tried to do that. And with my student Eliza, we are actually probing this epoch, like, beyond 3000 uh, days epoch. We requested for 4 supernovae with Chandra, and thankfully we got that time. And Eliza is just working on this for 3 months, but she has gotten some very interesting results. So the blue light curve is the one which is so far the best observed supernova in X-ray band, and it has a best column density plot. And you can already see that at 3000, this column density would have been lower than 10 to the power 21 centimeter mean square. But the two supernovae which Eliza has analyzed and constrained, you can see the column density is already much, much higher. So we had picked these 4 supernovae based on infrared, and we thought that a new dust may be forming, and these are extraordinary supernovae with very high circumstellar interaction. And our prediction, I would say that NASA, we gambled, and NASA, understood that it's a gamble, and none of us knew about the results because it has not, no supernovae have been observed that late, but we did. And I think NASA should be very happy to see our results, that we are seeing such high column density. I hope she will finish the work soon and it'll get published soon, in few months. In radio, of course, this is very, it's always much easier to observe supernovae very, very late. For example, this is a supernova, again, a core collapse supernovae. If you see just on the left-hand side, we observed it from, like, we have a program of infant supernovae with ALMA, and we observe from few weeks to 200 days, and this is how the supernova is. And then we just happened to observe 3 years after the explosion, and you can see the rebrightening, how bright it has become on the right hand side. And we generally don't see those in supernovae because the density is going down as 1 over r square. So you should see the radiation also falling down with time. That's how the synchrotron moves. But we did see this, of course, increase, and but with just few ALMA points, we were able to not identify what this. We did publish this few years back, like in 2023, I think, yeah. But we were not able to just constrain the models. So so you can see on the left there could be any model which can fit in this kind of thing, and these are assuming different kind of density profiles. So my student Anika is doing the VLA and GMRT study combined with ALMA and trying to constrain these models. Again, she's just done this work for 6 months, and hopefully, we will do a modeling, detailed modeling, and this work will be, published soon. But this is like, a very detailed study. But we are already understanding that this kind of thing can come from a binarity, where a star which has binary, because of binary influence, it is losing much more additional mass, and this mass is kind of forming this shell. And when the supernova explodes, and at 1000 days, when it reaches the shell, it is encountering this extended higher density, and that is what is giving this kick in the flux of the supernova.
Um, One question, because this is radio emission, can this also happen due to the magnetic field in that region? For some
uh,
reason, it's enhanced in that region.
But you need a huge,
Hmm.
huge amount of magnetic field enhancement, because if you see the synchrotron flux, I forgot right now, but magnetic field dependence is, I think, 7 over 17. So it's not really that high. So you would need like crazy, crazy, crazy amounts of
I see.
enhancement, which we doesn't usually see. So it has to be related to
The
the
density.
star. And this is not the first thing. I'm also showing that there is another supernova, which, of course, We didn't study, but people have studied, and you can see that, initially you were seeing this regular synchrotron, and then one sees this very enhanced emission. And that can only be explained by binarity. Of course, there are new theories now where say maybe there is this pulsar wind nebula is, also showing emission, which is kicking off this additional emission. We don't know that that can do it, but this is one thing I wanted to, show that this is the most exciting one. So this was like a very 2001 EM. It was a very exciting supernova because, it was a supernova which had no hydrogen and helium in the beginning. There was no radio emission in the beginning. But then there was a Caltech group was doing this late time radio emission studies to see off-axis gamma ray bursts from this supernova, and then they saw radio emission at 3 years after the explosion, and the very large baseline interferometry showed that the shell was moving only at few thousand kilometer per second. So this was basically a density shell which had given rise to radio emission. And we decided to just study this in detail and combine all the data. So we thought we'll just take another data 15 years after the explosion. And when we took the data, we see this enhancement at 2 epochs. And this, if you model, this can be only if there is another density, you are hitting not just one density shell, but one density shell 3 years down the line, another like 15 years down the line. If you trace back into the time machine argument, this happened like few thousand years before supernova explosion, and 25,000 years before supernova explosion there was these density shells which are only most likely to come from the binarity. So anyway, so this is how we do these studies of supernovae, try to understand these progenitor histories. And of course, as I said, I already talked about the radio aspect, radiative shock, single temperature, but there are other caveats. When we do these studies, we assume the equipartition of magnetic field and relativistic electrons, which people assume all the time in galaxies and things. But supernovae are dynamic structures. There is no reason for them to be. But we have so shown in some cases that if you have, if you do a very wide band studies or if you have inverse Compton kind of thing, then one can constrain these microscopic parameters. But this has been done not more than half a dozen supernovae. So this is something one needs to do in detail. Other thing is the shocks are considered to be fully homogeneous, and that's how we derive synchrotron. We provide all these parameters, but that can actually not be true all the time because it's again a very dynamic system, and things are very happening at a very non-linear scale. So we had actually shown in 2019 in one supernova that a homogeneous model did not give physically viable values. It gave, we incorporated this inhomogeneity, and we were working with a Stockholm team, Bjornsson, class in Bjornsson, and then we understood this model, which was, how the flux will change if there are inhomogeneities. And this is a very toy model. Again, this field needs to move forward with better modeling and more detailed stuff. But we did see that, this kind of inhomogeneities are needed in the shock. The third thing, which is I think the most important part, is that if we always assume a spherically symmetric CSM, and these are density profiles. So we understand these density profiles, and we have only one line of sight to see on our Earth, and so it's difficult. But we also know that in enough cases, spectropolarimetry have shown that the mass loss rate may not be very spherically symmetric. And in that case, the shock will not move with similar speed in all direction, and it will be a function of line of sight. And the density profiles may look very different in each line of sight. So we are trying to do now a 3D simulation of supernovae, massive stars. Especially we are actually taking binarity into account, because binarity is the one thing which can cause asymmetry to large scale. So these are studies in progress here at Charlottesville we are doing. I wanted to just say that, summarize that we are trying to fill this gap by flash spectroscopy and X-rays and radio. And we currently have a lot of telescopes which are, because all of these things are a direct function of telescope time and how well you are studying these objects. And we do have a lot of good telescopes, but we do need to continue these science to, do good observations of supernovae. And I guess I'll end here.
Thank you so much, Poonam. Any more questions? I mean, I know that I and Manami both already stopped you several times.
No, I enjoy that. Yeah.
I have a question. Hello.
Sure.
Yes, please go ahead.
Hi, this is Shubhrata. I have a question that we are able to decompose the radio spectra very easily, I think. So can we kind of extend to X-ray as well, having some hook between the two and then able to decompose the X-ray as well?
So X-ray and radio emission are coming from very different methods.
Sources.
Sources are same, of course, but X-ray is not synchrotron. In some cases, in gamma ray bursts, we do see synchrotron X-rays coming, but in supernovae, X-rays are almost always either thermal or inverse Compton. So the same physics doesn't work, and also collecting X-ray photons is so much more difficult than radio photons that you always have, much lower X-ray photons to be able to do any detailed modeling for X-rays. Yeah.
I see. I see. Thank you. And one more question, maybe very naive, because in star-forming galaxies, I model the radio spectra, and then majorly I'm seeing that the low frequency band turnover is very much attributed to the free absorption. But again,
Galaxies.
yeah, in galaxies, star-forming galaxies, let's say in
Okay.
like very starburst galaxies, LURGs, ULURGs, infrared bright galaxies. So I model the radio spectra, and majorly I'm seeing that the low frequency turnover around 54 megahertz or something, with contribution from a LOFAR. The attribution is majorly, yeah, from free. But it was interesting to see that we have supernovas, and then where the
Yeah, that's
synchrotron
true.
self-absorption is majorly,
Yeah. So
yeah.
once you take care of synchrotron self-absorption, which is an internal effect, then whatever is left has to come from external medium, right? But since the densities are much higher here, you will see the turnover at much higher density because absorption is proportional to lambda square. So your star-forming
Yeah.
galaxies still have lesser density of the medium, so they are actually peaking at lower frequency, which is actually extremely interesting because we did, try to do some supernovae with LOFAR with some collaborators in Stockholm, and it's the kind of science one can get at lower frequencies for some of the old supernovae, like 93J is amazing. So yeah,
Yeah.
okay. So you are at Netherlands in
No,
Amsterdam, or?
no, no. I'm currently in Poland in National Center for Nuclear Research. I'm a postdoc here. So
Oh,
yeah, this was my PhD project, majorly studying the radio continuum of star-forming galaxies, etc.
oh,
So this
okay.
is quite interesting that when we go in a much more spatially expanded scale, it's synchrotron self-absorption which is majorly dominating. So
Yeah,
yeah,
that's
this
true.
is, yeah. Thank you so. It was a very interesting talk. So thank you so much.
Thank you. Yeah.